In the last module, we saw that atoms in a lattice or in a crystal are placed in a parabolic uh, potential with respect to its neighbors. So, because of the parabolic nature of the potential, each atom is a kind of a harmonic oscillator, or each ion in a crystal can be considered as a harmonic oscillator sitting um, in a potential well which is parabolic in nature. So, in this module, we would have a look at coupled harmonic oscillators or coupled oscillators, and we would introduce the concept of normal mode. So, this is a small kind of summary of normal modes, a concept which we would use in the next modules to explain vibration of lattices or crystal vibrations in solids. So let's start with it. Just to let you know that this module has been taken from a chapter in a book called Waves by Morin. I will share this chapter on LMS. Let, let's look at a mass spring system. So you have a mass connected with a spring and a wall, which is a rigid wall, spring connected with that rigid wall in turn. So K is the represent a spring constant. It's not the wave vector here. It's rather a spring constant, which determines, which characterizes the spring or the hardness of the spring, and this mass can oscillate about its mean position. So if it is displaced from its position, you would call this displacement as x1, where x1 is the displacement from the equilibrium position. So x1 is not the position, but rather the deviation or the displacement from the equilibrium position of this mass. So, and this displacement can be in a positive direction from the equilibrium point or in the negative direction, depending on any, let's say, any reference direction you have chosen. So it doesn't matter which direction, it can be positive or negative depending on your reference. So we can write for this mass Newton's second law F equals to ma, and to find this, so the acceleration in this case is the second derivative of this displacement with respect to time. So this, the two dots here represent uh, um, the second derivative with respect to time of x1, where x1 is the displacement itself. So this would be the mass into acceleration part of the F equals to ma, and on the right hand side we look at the forces which act on this mass, and the force, if we ignore, let's say, gravitational pull downward, uh, is the only force is the spring force, which is given by the spring constant k multiplied by x1, where x1 would be again the displacement, and a minus. So the minus sign tells you that it's a restoring force which create oscillation. So any force which has this form uh, would create oscillations in a system. Uh, okay, let's consider another identical system. Again, the same mass, say exactly identical spring connected with another rigid wall, and let the displacement of this other mass be x2 from its equilibrium position. Again, it can be a positive or negative uh, displacement, and one can write F equals to ma for this system as well. So the springs are exactly the same, so this would be this k would be the same, and x2 in general, or its second derivative with time can in general can be different than the second derivative of x1, uh, and we get a similar equation here. So what are the solutions of these equations? So these are eigenvalue problems, both of them, and we well know their solutions. Uh, so there are sinusoidal solutions in time. So the displacement of mass 1, or this mass, is a function of time, and an oscillatory function of time with a certain amplitude of oscillations. And a similar solution can be written for the second mass, again an oscillatory equation in time. Uh, what is omega? Omega is the natural oscillation of that frequency of the system, and it's given by the spring constant and the mass, more specifically the ratio of the spring constant and mass, taking as a square root. So this would determine the natural frequency of the system. So uh, this is a well-known problem, as we know. So we do have two spring systems which are not coupled to each other, rather they are independent systems, exactly identical, have identical solutions, have identical natural frequencies. Let us complicate the system a bit and introduce a system where there are two masses connected with spring, but the masses are now connected by a third spring. So you have these two springs with spring constant K as before, and now I have introduced another spring between these two masses. And for the case of making thing a bit more understandable, I would take this spring with a different spring constant as compared to the other one. Later on, you would see why I do this, but this helps us in understanding the end result of the system. So this is a kappa with a spring constant, which is that of the central spring, and the side spring are represented by k, a spring constant k's. Masses are again identical. So let's try to solve this system mathematically. Uh, so first we look for displacement, and again we have a displacement of this mass represented by x1, and the displacement of this mass by from its equilibrium position represented by x2. So these are again displacement or not, and not positions. So let's write the F equals to ma for this mass. So you would have the first term. So this spring, you have ma on the left hand side, and the acceleration is the second time derivative of the displacement x1, equals to the force on this mass, and the force on this mass is from the on the left hand side is from this spring, and that would be simply minus kx1 as we saw before. So if x1 is positive, the force would be negative, or if x1 is negative, the force would be positive. So well and good. What about the force from this spring? So let's look at this situation a bit. Let's say mass m, this mass displaces in this direction by x1, and at the same time this mass uh, displaces by x2, such that x1 and x2 are exactly the same and in the same direction. So what would be the force on this spring on this by this spring on this mass? So as you can see that if both of these are moves by same distance in this direction given by these arrows, this spring would be unstretched or uncompressed. It would be and it won't apply any force on this mass. Neither it would apply any force on this mass. So what matters now is the difference of these two displacement. For example, if x2 is larger than x1, which means that this spring is um, stretched, and if x2 is smaller than x1, so this must, for example, this must move more in this direction, and then this one moves in this direction, then this would be compressed, and in either case there would be force in this direction. So what matters, so the force on this would occur if there is a difference between these two displacement, and that term we write in this form. So because this spring is represented by kappa, another spring constant, and the force would be proportional to the difference of the two displacement x1 and x2. The larger the difference, the larger would be the force, and of course it would again be a restoring force. So you can look out this this direction. So if x1 is larger than x2, which means that this moves more in this direction than this one, so this spring would try to apply a force backward, which is on the left hand side, and this minus sign would represent a force in the negative direction, x direction. So the signs here make sense. Now let's move to this other mass. If it has a displacement x2 on it, then the MA part would be given by the left hand side, and then it would have a force from this spring, which has a spring constant k, exactly the same way we had before. And depending on the displacement, the force might be in the positive direction or the negative direction. So this is represented by this minus kx2. What would be the force from this spring on this? Again, it would be given by the difference of this the two displacement, which is x1 minus x2. But in this case, it would be the force would be opposite to what the force would be on um, this first mass. So this term would um, reverse. These two terms would reverse its position. You can check out by uh, intuitively checking the directions, which by putting in here a displacement. So these are the two equations which we derived for, or which we made for these two displacement of the two masses which are connected by a spring. So these are coupled oscillator systems, and these equations are differential equations and coupled differential equation, because in this equation of x1 you also have x2 in there, and for x2 you have x1 in there as well. So they are not ordinary differential equations, rather they are coupled differential equations. So let's try to solve these, and to solve this I would try the same kind of solution I tried for the separate spring system. So I would kind of guess a solution or estimate a solution of a certain kind. uh, so an estimated solution is usually called an as ansatz solution, which is an educated guess of a certain system of differential equation, for example, in this case. So these are my guess for or ansatz solution for this system, where x1 is given by with as a function of time, such that it is an oscillatory function multiplied by a constant a1, and similarly for x2 as a function of time as well. The question is, what is omega in this case? Because omega would be uh, the main point here. With what different frequencies can this x1 oscillate? For a simple spring system which were not coupled, we already know is simply k by m square root. That would be the frequency. But for this system, it's no longer trivial, and one has to work it out. So let's build upon this. Uh, I can rewrite these two sets of solution in such a matrix form. Uh, Looks a bit easier to manage this way. So let's put these solution, for example, these solutions into these two equations. So first, let me put these two solution in this equation. Take the second derivative of x1. I have, so one time I take the derivative, you have omega. Second time you take the derivative, you have omega squared. And because you have twice i's in front, so you have a minus over there. So minus m omega square a1, which comes from this term. You have minus k x1, where x1 is a e raised to the power I omega t, and minus k into these two coefficients. And of course this phase, which is ei omega t, it simply cancels out on either side because it's common both with a1 and a2, x1 and x2. So this is the first equation using these two ansatz solution, and this is using that ansatz solution, and I put it in the second equation, and that's exactly what I get. So this set of coupled differential equation have no take an easier form. Let's try to write them in a matrix form to make things a bit more uh, systematic. So the left hand side can be written this matrix form: minus m omega square multiplied by a column matrix a1 a2, or a vector. So minus m omega square multiplied by a vector, in which case the vector has two components, a1 and a2. There's a bracket here, this is some extra bracket, equals to the right hand side would be then given by the same vector multiplied by a matrix. So the matrix is given by the spring constants k and kappa, and a combination of them. I can rewrite, so I can move this term on the left hand side, and what do I get is this big matrix multiplied by these vectors a1 and a2 equals to 0. So that's a kind of a neat equation, set of equations which I get here. So just to let you know, a1 can be in general uh, a, a complex number, so it need not to be in a, a real number. So later on we would see it's really a complex, these are really complex numbers. But anyway, this column combination of these two complex number can be written in this vector. So we do have this two mass systems which are coupled, mass spring system which are coupled, and systems, and we have these equations for them. So just by looking at them, you can multiply the inverse of this matrix on either side, and you would get your trivial solution, which is a1 and a2 equals to 0. Of course, this is a trivial solution because it satisfies this equation. So but this is not a very meaningful result, because this would mean that both these masses are exactly at their equilibrium position and they don't move. So not very interesting. Let's go to a more interesting solution. And how do we find an interesting solution? So to find a solution, you multiply the inverse of this matrix on either side. That's what we did for this case. Um but if this procedure gives you only a trivial solution, then a non-trivial solution can be obtained if you assume those conditions for which the inverse of this matrix would become undefined. And if you remember the inverse of a matrix, it um, includes some cofactors divided by the modulus of a matrix itself. So if the modulus of the matrix becomes 0, the inverse become undefined. So that's another way of finding the solution for such set of equation, is to find the conditions for which the modulus of this uh, for which the determinant of this matrix becomes 0. So, and that those condition, that determinant equals to 0, would give you the non-trivial solution for this, for these coupled equations. So that's the modulus equals to 0, and it gives me such an equation equals to 0. I can rewrite them in this differential form, in quadratic form, and it gives me two solutions. So either omega squared equals to k by m, or omega squared equals to k plus 2 kappa by m. So these are the two values which omega squares can take just by uh, taking this condition for non-trivial solution. So if two values of omega square suggest that omega can have four values, and these values are given by a square root of these, plus minus k by m square root and plus minus k plus 2 kappa by m square root. So these are the four frequencies which our coupled differential equation give us. mathematically. So what do they mean? Uh, so first let's put omega square equals to k by m into this set of equation, and it gives us so you can put omega square equals to k by m in this matrix, and it this set of equation it becomes something like this. You can so a1 uh, minus a2 equals to 0, which gives you that a1 equals to a2, which in turns mean that a1 and a2, which can be any complex set of any complex number, uh, are directly proportional to 1 1 because both have similar values. Now put omega square equals to k plus 2 kappa by m into this equation, and what do we get is an equation like this after simplification. And minus, so the first equation means that minus a1 minus a2 equals to 0, or in other words a1 is equals to minus a2. The second line would give you the same condition. So in this solution of omega squares, it represent those cases for which these two coefficients have opposite sign, or in other words a1 a2 is proportional to 1 minus 1. We don't know exact values of a1 a2, but we only know that in for this omega squared value, both have the same sign and are exactly similar, and for this value of omega square they should have opposite sign. uh, Let us do a certain definition. From here you can see that this frequency, this omega, is smaller than the magnitude of this omega. So uh, this would represent slow oscillation, and this frequency would represent fast oscillation. So we defined two quantities. Omega s represented slow frequency given by k by m, and omega f represent a fast frequency equals to k plus 2k by m, because simply it is a larger frequency in magnitude as compared to this one. So after we do this, so what we do have four values of omegas, mathematically speaking, plus minus omega slow and plus minus omega fast. So, and this equation, as we saw earlier, in for this solution, type of solution, a1 and a2 are directly proportional to 1 1. So maybe we can put an equality sign here and multiply a factor c here. So in this case, a1, if a1 is c, a2 would be c, and c in general a complex number. Uh, but for this type of solution, a1 and a2 have opposite signs. So if a1 is c, a2 would be equals to minus c. So let's write the general solution for these cases, considering we have these four different frequencies in the system. So let's write a general solution by a linear combination of all the frequencies we have in the system. So for x1 as a function of time, the general solution will be given by something like this. So we have c1, a coefficient c for the slow frequency, the positive slow frequency, c2 for the negative slow frequency, c3 for positive fast frequency, and c4 for negative fast frequency term. So this summation would in general give you uh, a general solution for the, the left mass in the system as a function of time, so or its displacement as a function of time. You can write a similar term for x2 as well by utilizing this fact that for this solution, which is the slow solution, both the coefficient have the same sign. So if this is c1, this should be c1 as well. This is c2, this should be c2 as well. But for the fast frequency terms, which are these two, if this is plus c3, this should be minus c3. This is plus c4, this should be minus c4. So these are your generalized solution for x1 and x2. Now, to make x1 and x2 meaningful at all times, both should have real values, and you can have real values only if C1 and C2 are defined in such a way that C1 is equal to conjugate of C2. So let's say if in general they are complex numbers, so they would have some constant uh, which may be a real number multiplied by a phase. So this would represent a complex number. We have 1 over 2 over here just to make the finest solutions look a bit simpler. You would see in a minute why is this the case, but uh, just multiply by 2 of a real number, dividing a real number by 2 just doesn't do much harm. So uh, this is the kind of so coefficient we can in general talk about. So if you have C1 and C2 such that C2 complex is equal to C1, then the sum of these two terms would give you a real value. And similarly, if C3 and C4 are complex conjugate, then the sum of these two terms would give you a real values, and the expanding the exponent, the complex term would cancel out. So to make these two solutions real, uh, these conditions should be satisfied by C1, C2, and C3, C4. So once we do this, you can see what you can put C1 in here and C2 as well. So C1 would be AS, where AS may be some coefficient of the slow frequency component by 2, and 2 is just a number divided here. Uh, you have the positive phase of the slow frequency multiplied by the constant phase phi s plus C AS by 2. The frequency slow frequency component and the phase, and since C2 should be complex conjugate, there's a minus over here. And similarly, a F represent a coefficient for the fast frequency one because they represent the faster frequencies, uh, and the phase corresponding to the fast frequency. So the phase may be different for the fast frequencies AF and so on. So this would be X1, and similarly you can have an X2 solution as well. The only difference here would be there is a minus over here and the rest stays the same. So this term, the phase would be I omega is I into omega is t plus phi s, and in this case it would be minus I into omega is t plus phi s. So you can expand these into cos and sine, and you would see that the sine which comes with a complex number with it, they cancels out, and you're only left with the cos uh, part of the solution. So that's why you have a real solution here. Similarly is the case here. For these two terms, you would have a real solution here, and and the complex part cancels out. So the two set of displacement turns out to be something like this. No, this 1/2, because you have added the two 1/2s, you are left with only AS here, and similarly you are left with AF, which is the coefficient of the fast component. These two are real numbers, and the phase has been included in this phi s in this bracket here. The phase is this constant phase phi s and phi f. Uh, they are given from the starting condition at t equals to 0. So these are your solutions for the coupled spring systems, or specifically the time-dependent displacement of the two masses of the coupled spring systems. So let's see what each of these terms mean. So first, let's take the coefficient of the fast component as 0. So It turns out that if AF, you take AF equals to 0, then in that case x1 is exactly equals to x2, and that's equals to this cos term over here. And this only include the slow frequency, and the fast frequency component is just become 0. What does this mean? It means that practically means that, let's say, if x1 is positive towards right direction, x2 would also be in the positive direction by the same with the same magnitude. So if this mass is displaced towards right by a certain magnitude, this mass would be equally displaced by the same position, and uh, some other time you can have a displacement of this mass towards the left and displacement of this mass towards the left with the same magnitude. So this kind of part of the solution represents such kind of oscillatory motion in which both these masses move in tandem either towards right or towards left. Uh, Remember, so in this case, because both of these move by same magnitude, this spring doesn't come into play and doesn't apply any force on these two masses, neither in this case. So what happens that in this part, only the side springs, which are represented by the K's, only they take part in it, and the oscillatory frequency is only given by these this side spring, and the center spring has no role to play in this mode of vibration. These modes, which are collective mode, this omega s, which is given by this, and the amplitudes of the two masses, which is equal. This in turns defines something which is called as a normal mode. So for a normal mode is a mode of oscillation which is a mode for the whole system and not for a single mass. So this would represent the oscillation of the system such that you know the relationship between the individual masses within the system. So both the frequency and this relationship, it specifies the normal mode itself. So normal mode is a vibrational frequency mode, which is a collective vibrational state of the system. Similarly, you can take this S, which is the coefficient of the slow frequency equals to 0, and it turns out that in this case, if this equals to 0, so this part goes to 0, and then x1 has an opposite sign to x2, which is given by the cause of this fast frequency component. And the fast frequency, as we derived earlier, is given by k plus 2 kappa by m, so it includes the spring constant of both types, the one at the side and the one in the center. So what does this sort of motion represent? It means it represents that, let's say, if x1 is negative, which means that, let's say, if x1 displays in the left hand side, then x2 should be on the right hand side because it has opposite sign at exactly at the same time. Similarly, if x1 is towards right, x2 should be towards left. So these frequencies, these sort of oscillation are represented by this frequency, which is again a normal mode of the system defined by the magnitude of the frequency and the relationship between the coefficients of between the displacement themselves. Now this frequency, it has not only the side spring constant, but it also has the spring constant of this central spring which connects the two masses. And this frequency is larger than the slower frequency simply because each of this mass has two restoring forces acting on it, one due to this spring and one due to that spring. In this mode, this restoring force was missing. So when the restoring forces are larger, the frequencies are larger. The frequency One benefit of defining this normal coordinate is that you can now represent a system of coupled harmonic oscillators to a system of uncoupled harmonic oscillators normal using these normal coordinates. So you have these two equations in which these normal frequencies are completely decoupled. So you have an uh, uncoupled harmonic oscillator represented by this normal mode, and another uncoupled harmonic oscillator represented by this normal mode and normal coordinate. So this makes the maths a lot easier if you define these normal coordinates in this way. Let's expand this treatment to three masses. So I would go a bit quickly over it. So now I have three masses connected by spring and connected to the walls, rigid walls. And for simplicity, I'm taking all the springs constant to be the same. So let's say x1, x2, and x3 represent the three displacements. Each of one can have different displacements, and you can have F equals to ma for each of the systems. So for this first mass, which is on the left hand side, the mass into the second derivative of the displacement, which is the acceleration, equals to minus kx1, which would be the restoring force by the left spring on this mass, minus k into x1 minus x2, where x1 minus x2 is the difference of the displacement of these two masses. So this we have already seen before. This spring would only exert a force on this if there is a difference in the displacement of these two masses. So it's given by this term. No, you can also write the equation of motion or the Newton's law for this mass, which is mass number 2. It's given by this spring and this spring. So this spring would only exert a force on this mass if these two displacements are different, and this given by this term. And this spring would exert a force on this one if these two displacements are different, and it's given by this one. And similarly, on this mass M3, you have a force on it by this spring, which is kth spring, simply given by the displacement of the third mass, plus this extra term because you have force on by this spring on this mass, and is given by this difference of these two displacement, which is x3 and x2. You can check the signs are correct or not. Should be okay. You can again have an unz solution or an guessed solution for such a system, such that x1, which is the displacement of the first term of the first mass, is given by a1 e I omega t. Similarly, x2 by a2 I omega t, and for x3 equals to a3 e I omega t. To make things a bit simpler, because you would frequently encounter this k by m, so I represent k by m as omega naught square, which is simply the omega squared of a single spring system, just to make the calculation a bit easier. Now you can put these solutions into these sets of coupled differential equation, and you get an equation like this after simplification. So you get this matrix uh, consisting of omega squared and omega naught square, which we defined in this way, multiply by an a vector, and this gives you a null vector on the right hand side. So then you have to find a solution for this equation, non-trivial solution, and you turn out for the non-trivial solution you have taken determinant of this matrix and put it equals to 0. Determinant gives you such an expanded term from which you can take binomial or quadratic terms as common. So the solution of such non-trivial solution of the coupled system is gives you omega squared values of uh, these two forms, either omega square equals to 2 omega naught squared or omega square equals to 2 plus minus under root 2 omega naught. So these gives you this term, which is omega square equals to 2 omega naught square. It gives you two frequencies, plus minus under root 2 omega naught, and this gives you four frequencies, one for a plus sign and one for the minus sign. So plus minus square root of this whole thing, omega naught, and plus minus square root of this whole. So these are the frequency which you mathematically get from solving this type of equation for non-trivial solution. Uh, you can put these equations, these omegas back into this system and see, or omega squared rather, into this equation and see what values of what relationships you get between A1, A2, and A3. So let's do it for this first set of frequencies, which is omega square equals to 2 omega naught square. So for this, you can do the whole calculation just like we did for the two mass systems, and it turns out that A1, A2, and A3 for this kind of a solution is simply proportional to 1, 0, and minus 1. Um, Similarly, you can do the same for this solution with a plus sign here, and with the plus sign, this A1, A2, and A3 has a relation 1 minus under root 2 and 1 with each other, and the one with the minus value here, you get 1 under root 1 here. So you can easily see here what kind of solution each of this omega square represent. For example, if you look at this one, it would represent that this one, the first mass, it moves, let's say, if it displays in the positive direction, the second mass won't move, and the third mass would move to the left direction. So this would be this solution would represent that kind of a oscillatory motion in this system. Let's make it a bit better. So you have these three different magnitudes of frequencies you have in the system, in which one equals to under root 2 omega naught, the other is 2 plus under root 2 omega naught, the other is 2 minus under root 2 omega naught. This frequency is medium between these two frequencies. So this, the one with a plus, this would be the fast frequency, the one with the minus would be a slower frequency, and this frequency, which is simply the under root 2 times the natural frequency of one spring system, is the one in the middle. So that's why fast, slow, medium, these three magnitudes, they represent three different normal modes of the system, as we saw earlier. So from we can work out the time dependent solutions and the real part of it. So we can do the same process as we did for the two mass system, and it turns out that the real solution of x1, x2, and x3, which are the displacement of the left mass, the center mass, and the right mass, are given by this condition. So you can see the coefficient have a certain relation. The AM coefficient, for example, for this omega m case, where omega m is the medium frequency, has the combination of 1, 0, and minus 1. So here it is AM, here it is minus AM, and here it is 0, exactly what we saw there. Similarly, AF, which is the coefficient of the fast frequency component, would have a 1 minus under root 2 and a 1, and similarly, which is this one, and this slow frequency has a 1 under root 2 and a 1 here. So let's work out the normal mode in the how does the normal mode solutions look like in terms of displacement. So if I take AF and AS equals to 0, in other words, if I ignore the fast and slow frequencies, these two frequencies, and only consider this medium frequencies, so the x1 is equals x2 is 0, and x1 equals to minus x2 at all times. So what does it mean? That the central mass, which is x, has a displacement x2, it won't move, it stays its own position. But if the first mass, if it moves to the left, the right mass displaces to the right, because they have opposite displacement. So this kind of motion, similarly, if it this one moves to the right, this one moves to the left, this is called as the this would represent this frequency of oscillation, which has the medium frequency. Then you have this other combination in which you can take only take the fast oscillation. With the fast oscillation is given by this, you can take the medium oscillation, and the slow oscillation coefficient is 0. If you do that, it turns out that x1 and x2 displacement are the same, and x3 is different by x3 should be the opposite direction and should have an under root 3, is it? So by putting these two equals to 0, you can already see what the combination of these amplitudes would be. So x1 should be equals to x3. So both should have the same magnitude and direction of displacement. But x2 should is has a negative sign, which means that it should be opposite by a different magnitude, and the magnitude should be 1 over square root 2 of the magnitude of these other two displacements. So what does it mean physically is, for example, if x1 is this mass is displaced towards right, this mass should be displaced towards right by the same magnitude, but this mass, which is the second mass, should be displaced in the opposite direction, and it should be opposite direction by a different magnitude. uh, and similarly, if these two masses are displaced towards left, this should be displaced towards right. So these are the collective oscillations given by this fast frequency component. Then you can also look at the slow frequency component by putting these two coefficient equals to 0. Again, it turns out that the first and the third mass, they have the same oscillation, so displacement. So this and this, it moves towards right. Let's say both of them move toward right with the same displacement. The middle one would move with a different amplitude. That amplitude would be under root 2 times larger than these two amplitudes. So uh, again, it would be in the same direction. So all these three masses would move in the same direction back and forth. In this case, two move in the one direction, one move in the left other direction. In this case, one does move in the two side, one moves. So these three are the normal modes of the system, represented by these three values over here, which you can find for this system. So again, these three frequencies are normal modes because they are collective oscillatory modes of the system, and they in these modes of oscillation, all these masses within this system have a definite relationship between their displacement. So again, it's a similar system. So in principle, one can keep on adding more and more masses into this system to make this system of masses larger and larger, and that's what we would do uh, when we apply this concept of normal modes to a one-dimensional crystal, where in one-dimensional crystal you have like infinite number of atoms, and each atom is connected to the nearest neighbor by a bond, and a bond can be considered as a spring, for example. So you have a one-dimensional chain of infinite springs which are such that in which the neighbors are coupled with each other, and we would see there that you have normal modes like this appear in a crystal as well. So this is something which we would discuss next time in the um, next module. But the concept of normal modes, which is a collective oscillation of a coupled oscillation system, is important to understand, and that's what was this module intended to do. So just to summarize, if you have a system of two oscillating masses connected by springs and connected to fixed walls, then such configuration results into a formation of two normal mode frequencies, which are the collective oscillations of these systems, and you get the displacements, the general displacement of each masses via such a general description, which includes both the slower normal frequency normal mode and the faster frequency normal mode. So in general, if you look at a certain mass at any certain instant, its displacement would be defined by both these frequencies at any given time. And similar would be the case for the other mass. And going to a three mass spring system where three oscillating masses are coupled via springs or oscillators, then in that case you have three different normal modes, a fast, slow, and a medium frequency, and then you have the displacement of any one of the masses are then given by the a sum of the displacement by all three different frequencies, maybe with different amplitudes. So the rule here seems to be that the number of normal mode depends on the number of oscillating masses. The larger, so then the total number of normal modes would be equals to the number of oscillating masses in the system. So if we go to let's say a crystal system, and that's what we would do in the next module, then you can imagine that you would have a very large number of normal modes in there. So this module introduced you to the concept of how to mathematically solve coupled oscillatory systems, and that you come up with collective vibration modes of the system, and normal which are called as normal modes, and you can also define collective coordinates of this system, which are basically the normal coordinates. Uh, so these property this math which we did today and the concept of normal modes would be dealt with in the next module for a one-dimensional crystal.